Okay, good morning. I thought I will give another application of a more recent work we have done applying this averaging thermodynamics approach to a slightly different system than what we are used to work with. We are used to working with three-dimensional porous media. And I want to introduce two-dimensional continua. And so we'll see what the difference is. So I will first, given the facts you have had so many equations, first I'll go through some graphs and pictures to relax you a little bit, and then give you more equations. So these are examples of what I call, I will first give an examples of thin porous media, and then what is now different with thin porous media and standard porous media, the current approaches and why they have issues, and the new approach to do these, the modeling of these media to circumvent those issues. And I'll show the example. We have applied this to fuel cells and paper and to tissues, but I like the tissue example. So here is an example of a thin porous media. Some of you nod. I guess you have babies, so okay. So that if you cut it, you'll see that there are a number of layers there, and these layers are really put together loosely. So they are not forming a congruent porous media, I would say, or continuous porous media. And then there are the whole literature on modeling them, looking the moisture distribution through them. This is one example that we have done a lot of it ourselves, where we measure capillary. It's basically the same sort of modeling as you do for an oil reservoir. For samples, we determine capillary pressure saturation curves. Then we fit Van Genuchten formula or Brooks-Corey formula to it. From there, we can also get relative permeability. As far as I know, there are no measurements of relative permeability done for them. The saturated permeability is measured, and then Richard's equation is used to simulate it. And here's another example when they want to, in production of paper, they create this paper pulp, which is more than 90% water. And that water is not willing to leave the pulp to give us dry paper. They can do this with gravity drainage. Okay, that reduces it to 80%, but there's still a huge amount there. At the end, they have to heat it to get rid of the water, but that is very costly. So one of the things they do is that they put this paper through a press, paper pulp, but they put it on a felt material, which is porous, very hydrophilic, extremely hydrophilic, and there is the paper pulp there, and this is all thin layers, and these are actually very large horizontal extent, but also in length of this paper. This felt, the paper pulp goes over it. This is dry, extremely hydrophilic, and they pull it through these presses. The upper press is turning, and it goes through fast, few meters per second, and the press pushes the water from the pulp into the felt. So you get, this is an example of a very dynamic change of the saturation in this felt and in that paper pulp. Paper pulp is saturated. And this removes the water by half, it brings it to almost 40%, and then they have to do by heating remove the rest. And for this, they also measure capillary pressure saturation curve for this. It takes about 24 hours to get one imbibition curve, because as you know, they have to do it quasi-statically, and then they use it for the process that is really fraction of a second. The whole wetting occurs. Then they do all kinds of simulations, it's deformable, and so forth and so forth. There are thin layers of porous media in all kinds of filters. For example, when they filter the oil, or they filter and the oil has some residues that has to be filtered. In this case, we're talking about a gas filtering the air, and then there are oil droplets in there that have to be removed. So there are all kinds of layers in there, 2 different layers, usually a fleece type and a paper type, and the idea is that the bigger ones removed first, and then the smaller one are removed, so at the end there are only smaller ones leaving. I must say these are just examples I have taken from literature. It's not really that I'm very knowledgeable about them. There are all kinds of processes here. There are capillary forces, the issues are the same things that you have for porous media, the permeability and so forth. Now I guess another example is someone working on fuel cells here?
Me?
Yeah, huh? Mm-hmm. So you know fuel cells, they're also layered, and all kinds of hydrophilicity, hydrophobicity are involved, some of the features of these layers, for example, this is the gas diffusion layer, this is the macroporous layer. In all these cases, the thicknesses are small. For example, for the gas diffusion layer is somewhere about 150 micron in thickness. Macroporous is about 50 micron. But the issues that I will bring up later, for example, this thicker layer in conceptual term is thinner than this thin layer. And by that I mean this you can apply perhaps three-dimensional modeling approaches, but not to this layer. And I explain in a minute. So what I mean by that, I can use this. Yeah. Now, so what are the challenges? Now, first of all, there are many coupled nonlinear processes involved in all these applications I showed you. Often there is two-phase flow in this gas and water, for example, in filters or in fuel cells, in diapers, in the dewatering of paper pulp. There are many of them gas and water involved. Then we have multi-species transport and phase change. There could be evaporation involved. Often there is temperature involved. And then there are, in case of fuel cells, electron and proton transport could be. The clogging of pores can occur. The filters, this would be the case. In membranes can be the case. And in fuel cells, clogging of the pores, not so much by particles, by flooding of the gas diffusion layer can occur. And then swelling in some of these. This in diapers, we have that. In paper, we have that the swelling can occur. And this is an important feature that makes a large difference with three-dimensional porous media. We know is there is a space between these layers. And that space, I show you examples, it's not a porous medium, and it's not clear how you model it then. If you have in the reservoirs sand and clay and all kinds of layers, now there is no space between them. There is maybe a transition zone from sand to clay, but often we neglect that, and that is absolutely acceptable because you have got very large thicknesses, and then there is a small transition zone. Okay, you can neglect that, but or at some cases you can model it as an interface. It's still a porous medium interface, but here is a space. So for all these applications, we don't have anything but the three-dimensional two-phase flow problems. Multi-phase, multi-component. But one of the first issues is that you need to be able to define REV, representative elementary volume, to use your three-dimensional macro-scale equations. Every term in those equations is an average over a representative elementary volume. And if there is no such an elementary volume possible to define, so why shouldn't it be possible? Well, if you take 3D medium, that's my three-dimensional porous medium, when we apply the concepts of averaging, we basically, as you know, define an REV. So let's do that. And so, yeah, you can make it round or cubic. Let's say there is a, what is the color here? Is that visible? Yeah, an REV with a given size. Now, as you know, for this REV to be giving to you a representative average value must be much larger than grain or pore sizes. It has to have thousands of grains or pore in there. So which means that this R must be much larger than the pore or grain size, the microscale size. But also, when you apply this concept, the average quantities are assigned to the center of the REV. So you move this REV around, but then you cannot get it closer than half the size of the radius, closer than the radius, half the REV size. So the last point for which your macro scale quantities are defined is here, and then all the way around. Which means that if you talk about, see, when you specify boundary conditions, what does it mean? You say something about saturation field, pressure field, velocity field at the boundary and its relation to outside world. Now, this is the boundary, because that's where you define those values. So your macro scale domain is slightly smaller than your micro scale domain. You throw away this part. And once again, if this a capital R is much less than the domain size, let's say show it by L, then that's fine. I mean, what is it? We have a domain of a meter, and my REV size is a couple of centimeters. Well, that's acceptable approximation. But now if you go to, this is an image from a reservoir. It's not. This is coated paper. So you see the upper part is the coating material, is 20 micron, and the lower part is the fibrous base. There's another coating here usually, and that is 100 micron. The fibers, you can see them, they are 20 micron. So if you define an REV, it should really have sufficient pores in there, which means, yeah, you need, at least in this direction, 10 fibers. But I have only 5 fibers. So it's not even sufficient space in that direction to define But even if this was, let's say 10 micron, and there are cases that this is 200 micron. 10, okay, then that's one REV, that's one point, but then you cannot move it because REV goes out of your domain. Even if REV size is half of it, still then, yeah, you lose half your domain, because the domain you can define your average quantities would be from here to here, and use half of your domain. Interestingly enough, it's not too bad for the coating layer. This is the example also with macro porous layer and GDL in fuel cell, because this is 20 micron and the grains are only 180, 200 nanometer. So you have 100 grains over this thickness. Then yeah, there you can define REV and satisfy the restriction.
And some of the coated layer is only 10 composite micron.
Some places over that, that's variable. You mean it's
Well,
because
you
variable here?
Yeah, exactly. So
That's
there it
correct.
doesn't fit.
Yeah, so that's another issue. We have had, therefore, imaged a big section of the paper, 5 millimeter, I think. And then we have imaged this, and indeed we have given the variogram of this thickness. These other issues. This is of course a two-dimensional image. So that is this thing here. Behind it maybe it becomes thicker, but there are fibers sticking into this. And those fibers are because they add this in order to prevent too much absorption of ink by the fibers. They give this, that's why the glossy paper, this is coated, is the glossy paper. And then, but the fiber is nearby, that will actually absorb, is just close to the surface, absorb, swell, and cause all kinds of problems. So, yeah, that's definitely the case. So it's also heterogeneous. So here is the objection number 1. REV cannot be defined for torn field. So all the conceptualization behind our averaging concept, where we clearly define a restriction for the REV size, doesn't apply here. So continuum equations, I would say they are not applicable. Not in the thickness direction. In the other direction, we don't have any problem. Your REV is big enough, usually there is lateral extent is large. And yeah, so yeah, I think this is basically, I talked about this. This is an example of it. Then the second objection is that it's a matter of practical numerical modeling. You need to discretize this. So let's say we close our eyes and you say, well, I work with these macro scale equations, and I can say, who says that I need REV to define density? I will take many realization of, for example, this is a pore of the water that is in here, and if I take a large number of the realization, then I define an assembly, what's that? Ensemble average. I don't need REV, I do it ensemble, okay. You can do that. Then the problem is now you have to do three-dimensional modeling. You need to discretize this. This is 200 micron, okay, 10 grid cells, 20 grid cells, 10 grid cells, now 20 micron. In this direction, you have 20 centimeter. So now you either have to, in that other direction, have grids that are either very elongated, and I'm not a numerical expert. I have been told that this will give you problems if it is 20 micron in one direction and 20,000 micron in the other direction, 20 millimeter. That is 1,000 times flat. They give you numerical problem. Are the numerical experts here? Is that the case?
I think you might get this excess diffusion along the paper more than across it.
Right. So it can give you numerical artifacts.
Yeah.
So that remedy is in this direction to also make it the grid cells up. Okay, maybe 5 times the other size in that direction. That means you need a huge computational effort because the grid cells should be very small to match this size in that direction. So that's a huge computational effort. Of course, in return for that, we get a very detailed saturation distribution. Every 10 micron, we have a saturation value, and in the other direction, but actually often for all the practical applications, I have talked to these people, they say they don't need that. In diaper, they only need the average saturation. So there you make a lot of effort and you get all this detailed saturation, which is, then you throw it away, you average it. So why not work with the average quantity? And then there is that when you model three-dimensional, then you really need properties over this thickness. And numerically, you have to discretize in order to be solved, but actually, potentially, these different grid cells have different properties, but those are never measured. Really, we always measure layer average. I mean, if you take permeability in this direction, it's not going to be every 10 micron permeability measure. An average permeability. Capillary pressure saturation is average over the thickness. So we only have an average quantity, and we really need, as a function of the space, and we don't have it. So, the whole issue of 3D is because of heterogeneities usually, and that doesn't, we don't really provide that. And this is one of the most important objections. As I said, there is a space between the layers, cannot be modeled properly. You have this space in many applications. Here is, and okay, that this space is important. I like to show you this little experiment we did. It's just a rough experiment to illustrate the concept. Is that we took a paper of thickness of 240 micron thick, and we put a stain on it. And this is, I can't remember, we had the volume, it's a few microliter. And this stain goes through the paper thickness. This extent of stain is the same on both sides. Okay. Then we take exactly the same material, they can give it to us, and these are 2 pieces of 120 micron each, 240 micron. We put exactly the same volume there on the top layer, and then we see that the bottom layer doesn't get as much. So we don't get the same distribution all the way through. What's the difference? The difference between them is that there is that space between them. And that influences the distribution over the thickness. We have done that actually. I thought I had it for another. And you can do this yourself. Take 2 pieces of tissue, put water on the top, not a lot of water. We're talking about applications like inkjet printing, okay. And then you will see that it doesn't go all the way through. It depends how much you press them together, of course, to influence the space between them, but you will always see that. The space makes an effect on that. Now here is two sheets are from diaper material, and the gap is 367 micron. The thickness of the layers were 400 micron, and these are not compressed. They just put them on top of each other. In this direction, they are also not homogeneous. There are some of these layers, they have an embossed area. So if you look from above, you see there are areas that is pressed together. So it's, and that they are sitting here, for example, on those embossed areas, and that is open. And you can push them together, then the space for a great part disappears. But I have experiments of this, on both of them, of this. Despite that, you almost don't see the space, it still affects the transfer of water. Because here, the fibers are continuous. Here, you put them together, but the fibers are not continuous. They end there. They have to restart. And so the water has to be passed by these continuous fibers. And so that affects it. So there are alternative approaches to 3D. An attractive approach is simply do full-scale modeling. We often, these are, you have the whole domain in front of you, as opposed to oil reservoirs. You cannot do full-scale modeling, but here you can. You have the whole layer. Okay, maybe over 20 centimeters, that's a problem to model all the pores. To model, so what I'm saying is that not the pore scale modeling we usually do as a research tool, but actually as a modeling tool of the whole layer. But then, then you need a huge number of pores. It's a major effort. With things like lattice Boltzmann, it definitely doesn't work, not yet, because it would be huge number of pores, or smooth particle hydrodynamics, or with pore network modeling you could, but one issue is that often these are fibrous, and I do not believe that concept of pore network modeling that we use, pore throats, pore body, apply to fibrous materials. So that's still, but one could try. It's just a lot of effort. But why not do continue modeling, but then acknowledge the fact that my REVs over the thickness is only one REV. And so that is what we call a reduced continua approach. We model these as interacting two-dimensional continua. So, and that's what I thought, okay, I would show another example of this averaging thermodynamic approach to this. So here is how you would develop it, that say, okay, we REV in this direction is simply equal to the thickness. You can take to be exactly equal to thickness, but if the thickness is variable, you may want to take an REV that is larger, and then average that so the REV size doesn't change, but of course the thickness changes. And now you can do the averaging over this. You can start at the Porous scale, write the governing equations of Porous scale and Grain scale, or we can do what we did in this course, start at the molecular scale. Why not? And then derive the conservation laws, and then use the thermodynamic approach to derive constitutive equations at the scale of interest, which is at the layer averaged scale. Now, we could start the molecular scale. I'm not going to go through, this has been done. We have done that, but I'm not going to go through that now. You know, familiar with particles, MI, VI, is the XI dt, the forces between them. You can do all of this, and then, as I said, the averaging domain is over this whole thickness. And if you do this kind of averaging, you get the same kind of conservation laws we got with one exception, there is no gradient in the thickness direction. There are only x and y gradients. As in an interface, you only have lateral in-plane gradients. So that means my thick layer becomes an infinitesimally, becomes a surface, a mathematical surface in my 2D continua approach. And then it is interacting with another mathematical surface. It's really like this. So your our continuum doesn't have any thickness in this direction at all, conceptually.
I mean, why do you take these exchange layers out?
I'm not taking them. This layer exchanges with this.
On the top to the bottom, you seem to indicate that you take the exchange layer out also.
It's just that as far as my two-dimensional continuum is concerned, I don't need to model it. I show you how I model it. The effect is there, but it's not part of my two-dimensional continuum.
Well, I mean, take for instance the exchange layer to be air, yeah, and the black, blue, and red layers to be a metal foil. Then the conductivity of the material in the direction normal to the surfaces is 0, whereas along the surface is the conductivity of the metal layers.
Correct.
So you cannot take this air out without changing the properties of the system.
I change the property of the system, but I don't model explicitly the air. The way I model the air is that, okay, there is a heat exchange between, and for that matter, mass exchange, between these layers. And that exchange is a function of what is in here. So this becomes a exchange coefficient that for the case of air is either 0 or extremely small. So I put an exchange coefficient that regulates the heat or the mass transfer between them, and that depends on the properties of this layer. Well, how do you get it? Not the same way you get permeability or heat conductivity by experiments. So maybe I'll show it and then you will see whether you agree to that or not.
For some of those models, it seems like this exchange layer actually has significant volume compared to the layers, and then it makes it molded too, doesn't it? To sort of have a saturation in there to say something about conductivity, for example, between the layers.
Yeah. Now the question is, what are the material properties you assign to it? If you say, I must say this doesn't include that. If you do that, okay, then I have another layer here. Then instead of 3, I've got 5 layers. That is correct. You could do that. Maybe you're right. Maybe for my own applications, I have been too much geared towards, I just model it the same way that when you have a fracture and a matrix in a 3-dimensional domain, you have an exchange between them. And you say, okay, there is an exchange term between them. Or if you have water in the pore, you have solid grain, you have adsorption. Now, you don't model that interface. You model it as an exchange domain. That's the way it's been done here. But no, actually, I must say you're right. You could add the exchange domain if it has a significant volume. You can put it there. Yeah.
The exchange domain will, in the fuel cell, have constitutive equations of its own, I think.
Between which layers do you mean? Because
between the electrode layer and the microporous layer, electrocatalytic layer.
Yeah. No. Okay. I fully agree. Any layer that has property should be included. Here I had the notion that I have my porous layers, and this is only a, in Dutch they say doorgeefluik. It just transfers.
But if it has significant volume layers,
We
it
can
might
add.
be the...
It adds to the
Absolutely.
complexity.
Now that you say, for example, if I've got here in filter, this is a paper material, this is a fleece material, and I'm filtering oil, and this is a reasonable volume. Now then you have a big volume of water, oil there, and this time it can store heat, for example. Yeah, that's correct. So yeah, it's just identify the layers and put them all in there. And because these layers have each their own property, now then you assign the properties there. Then we have to see whether those properties can be obtained for a given practical situation easily. I give an example of that.
It might be worth mentioning, since some of us are oil people, that this is actually the way it's very often done in reservoir simulation.
That you do
And you have this,
two-dimensional.
Yeah, you have this. You have this RAV problem. You have very thin layers, or very heterogeneous layers, and then you have some. Yeah. So basically, you tend to, in reality, in the reservoir simulator, you tend to model it in this kind of way.
Yeah, you could. I mean, it's
And
this.
you have in between those layers, you can have some shales, and then you have some multipliers that you put in. So this is very well known. I would say, well, not really well known, but this is, in reality, this is also the way one is doing it in the oil business.
So you mean lower permeability lenses between the big.
Yeah, so you can you have some layers. The layers themselves might very often it is impossible to find an RAV for them.
But these are the thin layers.
And then in between those layers, you may have some shales or some reduced permeabilities, which you don't model at all. You just model it as some reduced factor on how much can flow. So this is very well known as a pragmatic way of thinking in the oil industry.
But I thought in groundwater flow we have that aquitard, and the aquitard only provides a resistance to exchange of water between the upper aquifer and lower aquifer. Is that what?
That's
also
usually
mean?
what one does. Is add some resistance.
But then typically in those situations, in that aquitard there is no significant lateral flow, so they only assign a resistance to that aquitard.
Yes, so it's not modeled as a layer. But even
Correct.
My point is that the layers, even the layers themselves, do not have a RAV in the vertical direction. Very often in oil reservoirs.
Yeah.
So
you
basically,
don't-
you just model it as a layer,
But is there lateral flow in there?
Yeah, there's.
Usually
so
there is not. You don't model lateral flow in there. The closest you also get to this is if you have a fracture.
Oh, okay, I think
Because
you
the fracture
understand what
you-
I'm saying. I'm
Yeah.
saying that in the oil reservoir I have layers.
Yeah.
They are modeled at two-dimensional.
Yeah.
They are too thin to have an RAV in the vertical direction. So in reality, they are only modeled as two-dimensional.
That's right.
And then you have, between those layers, you often have shales, or reduced permeability, which is not modeled at all. You should model that as a reduced permeability or a reduced transmissibility between the layers. So you have transmissibility between the layers. So the
And
vertical direction is not in reality modeled in the continuum at all. It's just modeled that you have these layers, and this talks to this one, this talks to
They're
this
only
one, this talks to-
two-dimensional discretization.
Yeah, so, well, discretization, yeah. You only discretize, you can only think about the discretization in reality in the two dimensions.
In the two-dimension, yeah.
But because the sizes might be quite, I mean, the aspect ratio might be quite similar to what you're looking
Similar
at
to
here.
it, yeah. And then, how is the exchange regulated?
Yeah, that is the.
Okay.
Like this, yes. Finger.
Yeah. Yeah, I mean, of course, the concept of layering, as I said, in groundwater flow, especially when often the flow is horizontal, then even thicker aquifers are still modeled two-dimensional because in the vertical is almost hydrostatic. And then there are thin layers between them, they modeled as resistance. And it's very similar to this. That's the okay, so in fact, the governing equations we get is something you can write for that kind of layer. It's nothing special. The mass balance equation says that the material derivative, when you fix it to the layer, so I hope you realize this is the time derivative plus velocity of the layer in the horizontal direction times the gradient of this. So this is the material derivative. It involves density of the phase per volume of phase, the porosity of material per volume of fraction of the phase, so which is the volume of phase divided by volume of the pore, and then of the layers, of the material, and then multiplied by the thickness. Because we average over the thickness appears here as one of the quantities, variables. Now, this is the advective term. And then what is extra here is that each layer has a top layer, has a bottom layer, and exchanges mass with the top and with the bottom layer. And this you can write off to your hand. I mean, we don't need to start at the molecular level.
Why don't you use mass per unit of surface area?
Mass of
Per
water?
layer per unit of surface area. After all, you're integrating over the layer. Replace it by a two-dimensional entity. And on the two-dimensional entity, you have excess mass, as it is called, per unit of surface area.
Mm-hmm. But I'm trying to say, if you have water and compressible as mass density is constant, then I like to work mass of water per volume of water.
Well, I mean, yeah, whatever you say, but I mean, basically for transports, for two-dimensional surfaces, you use properties per unit of surface area.
And I think that is, here is the volume of, no, this is volume of the phase per volume of the layer. But I don't see what additional benefit it gives me. If I have mass of water, which is mass of water per volume of water, why should I make it per surface area?
Since you average over the thickness of the layer, what you basically get is the integral of the property that you are looking at over the layer.
Yeah.
Now, since that property is per unit of volume, after you integrate it, it's per unit of surface area.
Yeah, but I multiplied by B. That's why I need B explicitly out there. Because B changes with time, B changes with the space. If I do that, then I bury that dependency on that material per surface. I don't want to do that.
So basically, well, I mean, the density per unit of surface area can change because of whatever reason.
Yeah, but I'd rather break it into B times water density, which is known, and I can assume it to be constant. I mean, for me, this is advantageous because rho I can always cross out. But as soon as we say mass of water per surface area, I can, even for incompressible water, I cannot cross it out.
Yeah, but assume that you have ions, right, in the system, or salt, right? The density of the salt in the surface is not the density of salt in the liquid next door or whatever. So the sensible quantity is the amount of salt per surface area. I mean, to write that in terms of a density of some imaginary salt concentration in some imaginary three-dimensional fluid is not sensible, according to me.
Okay, I'm not sure we can talk about this, but to me, over the thickness, I have 10 pores. It has a volume. My REV has a lateral dimension, so I have a volume of water there. Then I say, okay, the concentration of salt is the mass of salt in that volume divided by volume of water. But, I mean, it's very well defined concept. And in fact, that's how I measure it. Using some sort of, we use here TDRs to measure water saturation.
But take for instance a surface tension. If you introduce a surface tension for this, that is pressure per unit of surface area, per unit, surface area.
But I don't have surface tension for the layer.
Yeah,
I have surface tension inside between two fluids.
The surface tension is an integral over the parallel pressure minus the normal pressure, say, right? And it is not the dimensionality of pressure, it's pressure times length.
So B times rho is the quantity you say, is mass per surface.
Yeah.
But I think B must be out there explicitly, because B is a quantity, can be constant in time or space, even if rho is not constant, which is compressible, and the other way around. Rho be constant and be variable in time and space. So if I make a choice, I would put B explicitly out there instead of burying it in rho. Yeah.
So for what is the thickness of the layer between water and water vapor?
The layer thickness is given, is dependent on what material is in there.
Water, say argon and argon vapor, right?
Thickness of layer, I assign it, actually, that's a whole issue. What is the layer thickness? How do you determine that? But let's say I determine it, then it doesn't matter what I'm defining for.
No, is it properly defined? Yeah. I mean, you don't need it either, because you can look at if there is any surfactant in the water, for instance, which goes to the surface. Yeah, then it is what counts is the amount of surfactant at the layer, not any density of surfactant in some imaginary finite layer.
But the surfactant is not accumulating over the layer, it accumulates in the interfaces between, say, oil and water within the layer, in the pores.
No, I mean, the hydrophobic tail is in the oil and the hydrophilic part is in the water.
Right, so they sit at the interface between oil and water. The interface between oil and water is inside here. It's not over this layer. It's not that I have oil here and water here and that's my surfactant accumulates there. So I'm not sure we're talking about the same thing.
Yeah.
I mean, I really don't want to sweep it away because I like to know what is it in there and learn from it. Absolutely, it's just I don't quite follow the surfactant has nothing to do with layer. This layer could be thin, could be thick. The surfactants are in the interfaces between the water and oil in this.
Yeah, but in your description where you have the lines or the planes, that structure has disappeared.
Yeah, this is not a surface like between air and water. This is just a piece of paper. And the surfactant doesn't accumulate over this thickness, it accumulates inside between the interfaces.
The only important thing is that it is much longer, so to say, your piece of paper than it is thick. It's like the atmosphere of the Earth. If you look at the weather forecast, they treat it as a two-dimensional system, right? Okay. Yeah, they have a pressure of that system. They don't have a pressure distribution. Bulk pressure,
exactly.
Right?
Yeah, I mean, so the same in here. I have one row, one concentration of solute over this whole thing. It's not the distribution, but it's one concentration.
Like if you have ions, for instance, on top of a colloidal surface, right? Okay. thickness of the surface is not defined by the thickness of the layer of the ions. There are many other properties that all together, give you a region between the inside of the colloid and the outside.
But this is not comparable to that surface. This is not a surface. This is a three-dimensional medium that I presented as a...
Well, which you presented as not being homogeneous in the direction normal to the surface.
I do.
Well, your picture of the paper had a finishing layer, for instance, which is clearly...
Oh, that would be 2 layers. That's 2 layers. Coated layer, coated paper actually is 3 layers. 1 coating, 1 fibrous, 1 coat.
Yeah.
So I'm sorry if I didn't make...
And everything is completely homogeneous inside the layer.
It doesn't have to. I just have one value for that layer.
So why replace it by a 2-dimensional system?
Because I'm not interested in those heterogeneities.
No,
I just don't need it. I mean, everything is heterogeneous. The most homogeneous sand layer is at the lower scale, heterogeneous. But I'm not interested. I model it as homogeneous. The layers, of course, they are heterogeneous over the thickness.
Yeah,
Even the fibrous material. I show you the fiber density we have measured. It's not constant. It goes like this. I'm not interested in that.
Since you say that they can be treated as homogeneous, you can just treat these layers as homogeneous layers, actual layers that are homogeneous, and do not go to the 2-dimensional description.
No, that's not true. I show you. I'll show you an example. Either we are talking alongside each other, then I'd like to really know that, or there's something you're saying that I do not agree. But let me show this. The case of, we have applied this to these layers of, 2 layers of diaper, and not diaper, sheets in the diaper. So the governing equations are for mass, you can write it for a species, and for momentum. Note that the gradients are only in the horizontal, lateral direction. They are in the planar direction. And there is an exchange of momentum between alpha phase and other phases in that lateral direction within the layer. So this is intra-layer exchange. And then there are exchange interlayer of the layer of interest, K layer, with K plus 1 and with K minus 1. And these are those, I denote them by top and bottom. This notation was never simple. And then the energy balance is all the same. We have an entropy inequality, entropy balance, where in addition to the net rate of change of entropy, all the other ones, the net rate change was 0. This is not 0. We have all these other exchanges. Exchange of entropy between alpha phase and other phases within the layer, and between alpha phase of my layer and the top layer and bottom layer. And then this says that exchange between top and bottom must be 0. Now, that's trivial for all these. And then the net rate of production of entropy says that all those terms, we add all the production terms for all phases and for all layers. That's one system. That has to be non-zero, non-negative. And because all these entropy, local entropy productions, their sum is not 0, but it was here, I think, is non-zero, I don't need to include them. This must be non-zero. So for all layers and for all phases.
One simple question. I have difficulty reading all this equation. Is there an entropy production also in the exchange between layers?
that is indeed, there is an exchange between layers that is here. That is an entropy production.
Yeah, okay.
As a result of exchange of a phase with other phases within the layer, and then entropy production as a result of exchange with the top and bottom. Correct. But the only thing is that, I must say, this is an assumption. All those exchange terms together, when you put them together, they give you a non-negative. They are not going to be negative together. So the exchange between top and bottom layer, the sum of it is not zero. It's not that if the entropy goes exchange between them, that still has a production of entropy. And that's why we don't have those in here. Okay. Then dependent variable, we're going to stop in a minute and then take a break. Then we have dependent variables. Now, the usual dependent variables, these are the free energy, the Helmholtz energy, entropy, stress tensor, heat vector, exchange of momentum between phase alpha and other phases within the layer, exchange of heat between alpha phase and other phases, exchange of mass. By the way, this is written for the case that the phases do not exchange mass with each other. But of course they exchange mass with the top layer and bottom layer. So those are unknown. And these are things that in oil reservoirs you say they have layers, but I asked how do they define the exchange between the layers? Now this is actually one of the unknowns. And the question is whether this approach will give us something. And then the exchange of momentum between top and bottom layer, exchange of heat between top and bottom. Then I also have as my unknowns the rate of change of thickness of the layer with time. These are all functions of x and time. And the porosity of the layer and the saturation of one of the phases. And these are functions of independent variables, which for a deformable layer is the densities of phases, the deformation tensor of the solid phase, the thickness, gradient of thickness, temperature, porosity, gradient of porosity, gradient of temperature. All the gradients are only planar gradients. Saturation is gradient, and the velocity of alpha phase with respect to solid phase. And we define for the Helmholtz free energy a limited dependency instead of all this full list, only on density, temperature, saturation, and potentially the thickness. Now, one thing I was wondering is that if I give you this system of equations and all these forces and fluxes, can you just write the classes Duhem inequality? What's the entropy production rate? What are fluxes multiplying forces? I don't think, because this is not done before, this is it. Can we write this offhand, just dream of it? Or by analogy with single phase flow? Or single phase material? I don't know. So that, when you put in all the time derivatives, you see that we have time derivative of temperature. This is the material derivative moving with the solid phase. The deformation rate, and so maybe we take a break now. Sorry about that.
Did you leave this on
You found an error. Very good. That must be plus. Wow, I'm impressed.
I don't know. I have no idea.
Okay, so should we take a break?
Fine.